be able to design further some simple measurement circuitry in our practical placement. I hope we actually will be able to work with on practice with real components when this restriction due to COVID will be removed. Well, so we review now some general concepts. I suppose that you already have discussed this topic and this concept with your teacher on electronic course, but still we repeat it a little bit to some extent. So speaking about the electronic circuitry, so we actually made them of a set of different components which are strictly defined, well, actually generally defined in so-called passive electronic components and active components. So up to passive components, so they are such components like resistors, which have the most important feature is a resistance and just measure it in ohm. So they provide us with a possibility to limit currents, to make one of the most important circuits. It's the simplest but very important is it's called voltage divider circuits and so on. So set the limits of the voltages from the outer sources. Capacitors is a passive components as well. They actually resemble some capacitance, and we may exploit all the features that capacitors possess, like selective transmission of the current independent of frequency, ability to store charge, ability to store voltage caused by the charge, and so on. And inductivity is chokes or inductivity. So as a part of next is a type of the passive components is so-called transformers, which are two chokes on the one base wound together. But chokes or inductors that resemble inductivities and not resemble but represent inductivity. They have an inductivity, and we may use some feature related to the inductivity behavior, like generation of the electromagnetic induction, electromotive force, like restriction of high frequencies, currents, and so on. Generally, for our circuitry, we must use the resistor and capacitor circuits, and they are actually more probably widespread. The circuitry based on resistors and the capacitors, and this is related mainly it's related to miniaturization of the electronic circuitry because it's quite difficult to make a small choke, small inductivity. We have to provide a certain number of wounds, so certain number of inner coils, and that's why it's quite difficult to make a very small inductivity of a sound size. The designers what are actually developing some kind of electronic circuitry for microelectronics, for chips, they don't like inductivities because it's quite difficult to make an inductivity using modern chip manufacturing technology, like a planar technology itself. In a circuitry, in the principal drawings, resistors may be marked as like that and like that. So the difference is that the bottom depiction is more typical for the ISO standard, for European standard, and this kind of marking is quite popular in the United States. The capacitors mainly have more or less similar symbol and inductivity too. Sometimes the first example of this type of resistor drawing very often used exactly in microelectronics because the inductivity is not used so often, and there is sometimes when you draw by hand there is a risk to mix a resistor depiction with the inductivity depiction, but when you design some microelectronic circuit with no inductivities inside, so then such kind of resistor marking is fine. But we usually use both of them, so it depends on when I took a picture from what source. Well, despite except of passive components, there is plenty of so-called active components that usually are instrument or devices with a nonlinear volt ampere characteristic or volt-ampere diagram. So the volt-ampere diagram is actually the dependence of the current through the device on the voltage over the device. And here is one of the examples of such active components. They often are made by semiconductors, and this is one of the such type of components is the diodes. So you probably should know, you actually should know quite a lot already about diodes. Now just remember that we have the diodes, the most important feature of the diode is a one direction current transmission. So when we have so-called forward voltage applied to the bias, to the diode, the current through the diode is quite high, and it's nearly not limited. Generally, there is some resistance of the PN junction, but it's quite low. So we may have a very high current. What is important for the diodes, we should always remember that there is some special so-called forward bias or forward voltage, VF, and we have to actually overcome this voltage to open the diode. When the voltage is less than forward bias voltage of the diode, the current will be quite low. So sometimes it may be neglected. So if we describe it in a very, very primitive way, so we actually have to draw this growing path from the VR. Yeah. Another when we switch a diode in a reverse direction, so the current will be very small. Still, it will be, and we name it a leakage current, but it will be on an order of microamperes, or maybe even less. And here, important how big reverse voltage we could apply. So if we apply too high voltage, the diode will break through, the breakdown happens, and the diode just burned out. Some of the diodes are specially designed to operate at the reverse breakdown voltage without any irreversible damage. Such diodes are called as Zener diodes and are used for the stabilization of the voltage, because independence when the Zener diode is at the reverse breakdown voltage, the current of this diode actually is unlimited. So it doesn't depend on how big current is. Independently of the current, the reverse breakdown voltage will be kept very stable, and that is the application of the Zener diodes. Another example of it, and what actually is not mentioned here, but we should remember, is that the diodes always have some parasitic capacitance that could be expressed as modeled as a capacitors that switched in parallel to the diode. The capacity is higher on the reverse voltage, and it's related to the distribution of the charge in the PN junction, but the capacity is always. That's why at high frequencies, the leakage current of the diode grows up, increase, because it's actually flow not through the PN junction itself, but it flows through the this capacity of the PN junction. And then we have to remember that when we have very high frequencies, that our diodes may work poorly, yeah, because they actually doesn't provide anymore this one direction transmission. So they become, for a very high frequency, they may even become unidirectional. So, we may increase, or maybe we may decrease the capacity of the PN junction if we use not just PN, two semiconductor junction, but the junction between P semiconductor and a metal. Such kind of diodes has higher leakage current than the usual one, but they has the lowest junction capacity as possible. And such kind of diodes are called by Schottky diodes. They are used exactly for the high frequency application. Another special type of diodes, it's a photodiodes, which actually when we may illuminate PN junction and then generate additional current charge carriers in a PN junction and control the reverse leakage current with a light beam, with a light. So the higher the illumination, the higher leakage current will be, and use such diodes as a light sensor. And there is diodes which are designed to emit light. Generally, every diode, when it's switched on a forward voltage drop, emits some light, but this light usually remains inside the diode. And if you speak about germanium on silicon diodes, this light will be in infrared region. We don't see it. Another type of materials like arsenide, gallium arsenide, gallium phosphide, and so on, and even more complicated with the three metals inside. They are often used to make such kind of light emitting diodes in a visible range. Another type of active component, it's a different kind of transistors. Generally, we have two types of transistors, so-called bipolar transistors and field effect transistors. For the bipolar transistors are typical current controlled device. So they have three. I hope you remember what the transistor is. I just wanted to note that the feature of the diodes, it actually works as a current key. So the ability of the transistor to pass the current through is dependent on the current through the base electrode. So let's remember we have three electrodes which name the collector, emitter, and the base. And if we provide the current through the base to the emitter, so then we will get a high current through collector, of course, at the conditions that there is some voltage source, which it could push electrons, could push current through the collector. The two types of bipolar transistors, they are named PNP and NPN, and it depends on how the transistor junction is made. So if collector and emitter are attached to the N-type semiconductor and the base to the P-type, so we have NPN type, and then we need to bias base with a positive voltage to cause base current to flow. And if we have a collector and emitter at P-type semiconductor, so then we have a PNP transistor, and we have to bias the base reversely. So we have to put a lower potential to the base, then to the emitter. The flow is like going through the emitter from emitter to base. In a circuit, in a schematic, the PNP and NPN transistor differs with this arrow, which actually just indicate what is a direction of the base flow to open the transistor. Now, generally, the volt ampere curve of the transistor looks like that. So when actually we increase the voltage, the current initially it grows up, and finally it goes to the saturation. But the saturation level depends on how big the base current is. So if we increase the base current, so the collector saturation current increase too. And for this picture, I wouldn't say particularly what type of transistor it is. But generally, so if you could imagine this, here is an example, actual example of the volt ampere curve set of some certain transistor. And we see that when the base current is small, so we have a very low saturation voltage, or collector saturation current through the diode, through the transistor. And when we add the bus current, increase the base current, so the collector current increase too. And of the order of magnitude, as you see, the base current here is the microamperes, but the collector current is the milliamperes. So it actually gives us possibility to amplify the current using the transistor. So it actually is controlled by a very low teeny current in base electrode, and it may cause the high current flowing through the collector electrode. What that also should be noted, it's important that actually the current which are flowing to the collector, we need something to provide this current. We should consider that when we allow the current to flow through base, then the transistor itself generates some kind of current. No, it is not true, and it just indicates that if you have some altered voltage supply or current supply, the transistor starts to pass this current by. Another type of transistors is so-called field effect transistors. The most popular of them now is so-called MOSFET. When MOS, it means the metal oxide semiconductor, the structure of this MOSFET transistor, and FET is field-emitted transistor. The operation principle of field-emitted transistor is actually, so actually this transistor has three electrons, three output, two of them are named drain and source, or source and drain. One is a source of electrons, and second is drain of electron, or source of current and drain for current. And the third electrode is named gate. Here, in the difference between FET field transistor and bipolar transistor is that the gate may be totally isolated, absolutely isolated from the transistor conductive channel, and due to this transistors has a very high input resistance in respect to the gate electrode. The idea of this transistor is that in attaching positive or negative voltage to the gate, we attract or repulse the charge carrier from the area between source and drain. And when the polarity is that way, that it attracts charge carriers, so then between source and drain, then the conductive channel appears between source and drain, and the transistor starts to pass current by. So the saturation, the volt ampere curve is quite similar to one of the bipolar transistor, and we see here the same drain to source voltage. When to say saturation of the current at certain draw to source voltage, and here we see that this volt ampere parameters it actually alters independent of what type of voltage is applied to the drain, to the gate. So the higher the voltage, the more current pass the transistor by. So some application of the active component, for instance, the application of the diode. The typical application of the diode is current rectifiers. So here the four-bridge full wave, so-called full wave rectifier, a bridged full wave rectifier is shown, and I think that you know quite good how it works. So actually these four diodes switched in a bridge allow us to let the current to pass through the load in only one direction. Generally, sorry. Generally, if the input of the bridge rectifier is an alternating current, so the output of the bridge rectifier it's no, actually one polarity, but highly pulsating current. So it pulsates. We name it full wave rectifier because every pulsation got negative, both negative semi-wave and positive semi-wave of the initial voltage is converted to the positive semi-waves. If we add the capacitor to the output of the bridge rectifier, so then this pulsation will be reduced by the capacitor because it's actually accumulate the current, the load, or let's say accumulate the charge at the peaks of the at the peaks of this waveform and supply some voltage and current through the road because due to accumulated charge in between when the voltage of the rectifier drops down. Here in this other example, how we could use a single or separate active component. So this is just an AC sound amplifier. So we have an input, the source for the input voltage, which comes from a microphone, and here we have an output to the speaker. As you see, the design of the circuitry is quite complicated, and really it's true because generally the design of a transistor circuitry, if you going to do it from scratch, absolutely, it's quite complicated, mainly because you need not just think about the general principles of how you get amplification using transistor, but just because you have to stabilize the transistor operating mode, to have a constant biases for the base current that actually you should to provide all the regimes and all the all the parameters of the transistor to be as stable as possible. This required to include different kind of temperature drift compensation circuitry, gain drift compensation circuitry, and so on. Another important thing that if we are speaking about such kind of complex circuitry, we actually still may divide it in a certain part. For instance, the part which is built up to around these two transistors is actually the so-called differential amplifier. And this is just an output amplifier, so-called bipolar output amplifiers that provide the current through the load. Yeah, and these two actually stages are connected one after another, and most unpleasant thing that the next stage may have some influence on the previous stage. So they call it, there is a kind of feedback between the next stage and previous stage are formed. And this is not very convenient for calculation, because if you are going to calculate very accurately, we have to take into account this feedback. Still, our destiny as a designer of measurement equipment or the prototyper of some laboratory circuitry for the measurement is now much more easier, mainly because of invention of this component, what is named operational amplifier, or in short, an op-amp. It's quite a complicated three-stage amplifier. The first stage here is a differential amplifier that reacts on the difference between two inputs. Then there is some intermediate amplifiers, and finally it has quite a high power. Yes, the intermediate amplifier, and here we have an output circuitry which provides quite a high output with a bipolar power supply. It's a bipolar output which could be more than 0 and less than 0. But to be able to exploit the operational amplifier in this mode, and the output may be both negative and positive, we have to feed this amplifier with a so-called bipolar power supply. So we have to have a power supply which has a minus pole, a plus pole, and some zero, the point between two poles. And in fact, in this case, the output will be the voltage, which may be both negative with respect to this average zero or ground pole, and negative in respect to this zero or ground pole. As you see, the design is quite complicated, but we don't need actually to go too deep inside this operation amplifier design, because as a user of such devices, we need how to calculate the circuits, how to design the circuits which use this operational amplifier. So one more. So this is a definition. So not a definition. This is a marker. How do we mark the operational amplifier on drawing? So we sometimes what is important. Sometimes it's absolutely necessary to show the so-called both inputs of this amplifier. A little bit later you understand why they're plus and minus, we discuss, and output. Sometimes the power supply lines sometimes are not drawn, so nobody draw it, because it's just understand from the context that yes, we have to connect it to the power. Nevertheless, if you are designing some assembly circuit or assembly drawing for or you design some drawing that you're going to use this drawing of the electronic circuitry to drive afterward some PCB design software. So then you of course have to indicate this all absolutely what happens for every leg of the chip. So then you do need to do it. In the principal circuitry, when you just draw them to explain how the device work, how the device electronic works, these power supply lines may be omitted. So generally, the operation of this operational amplifier. So first of all, what it is? It's actually symbolically we represent it, as I mean, by a triangle. Yeah, and of course, and actually, what this device is doing. So it has two input. So what is important? It has a two input. One of the inputs is named inverting input, another, as you understand, non-inverting. In the circuits, they are often in the drawings. They are often non-inverting input may be marked as a plus. Usually, inverting input is marked as minus, but sometimes maybe only non-inverting input may be marked with a plus. So if we know where the non-inverting is, the second is automatically inverted. Another example that sometimes we depict the inverting input with a small cycle around the input. We don't write plus and minus here, but we just add some kind of small cycle on the input. What is the difference between non-inverting and inverting input? When we add a positive voltage to the non-inverting input, the output will be a positive voltage too. If we put a positive voltage on inverting input, the output becomes negative. So actually, all the signals, all what we got on the inverting input will be transferred to the op-amp output with a minus sign. In fact, in general, the operational amplifier, it's a differential amplifier with very high gain, nothing else. So what does it mean differential? So the output voltage is proportional to the difference between non-inverting and inverting input voltages. So this means differential. So it's a DC, generally it's a DC amplifier, and what else? Yeah, and this amplifier has a very high gain. So this is actually the feature. So some example. One of the oldest and still operational amplifiers is 741. It's a single one op-amp. Usually it's manufactured as a single op-amp chips. Also there is a 742, I guess, where there is a dual chip, where there is a two operational amplifiers, and even you could find even a quad operational amplifier, so chip where there are four similar amplifiers, op-amps is placed. So this is a particular example of the 741. It's just general purpose amplifiers still could be used. Such a chip, the single chip of such kind of such amplifier has two special outputs for the 741. They are 1 and 5. Although it's not necessary that it will be 1 and 5, maybe 1 and 8 and so on. So it's a special output that is sought for the balance of the amplifier. So if you look back at the amplifier circuits, so you could see here, generally this input stage is actually is ready for the operation, but you still could find here two contacts, offset null and offset null, the first and fifth flag. Generally, why we need it? We needed to balance the output of the amplifier to 0 when the inputs are at the same voltage. Because here you see the input stage of the amplifier is actually so-called two current sources. So one current source and another current source, which actually we control it using non-inverting and inverting input. And so when we actually apply some voltage to the inputs, non-inverting or inverting, so some certain current start to flow through these two lines, let's say, and it's transferred further to the next stage. But the two lines of transistors, the first and second, they never will be the same. They always have a little bit difference. That's why when we apply the same voltage on both inverting and non-inverting input, we should suggest or should suppose, for the ideal case, that the currents through first and left and right, let's say, circuits, this transistor circuit, will be the same. This is actually not a fact. They are a little bit different because of the different parameter of transistors. That's why sometimes if we need a very accurate 0 at the output of amplifier, when we have a similar, when the input are equal, we wish to have an absolutely ideal zero of the output, we may a little bit adjust the conductivity of these two left and right paths by just but adding here shifting a little bit symmetry between these two lines, left inverting and non-inverting. We may shift it, for instance, by changing this resistor, 1 kilo ohm and 1 kilo. But of course, this is a part which is inside the chip, and it's impossible to do with the end user. It may be done on the factory, what actually is done. These resistors, they are a little bit, how to say, polished with a laser beam to control the thickness and to adjust the value of the resistance to have a as good operational amplifier as possible. Well, but in general, but then we may do it by connecting such kind of potentiometer between the first and fifth, or the A, or the 741, between first and fifth leg, and attaching the slider of the potentiometer to the negative voltage supply pole. Then by regulating, by adjusting the slider, we may actually a little bit change the potentials here, and that's why a little bit change the working of these two stages and make them more similar, you know, by just adjusting. So we couldn't adjust the resistor this one key and this one key, so we just add something out of the amplifier. What is important that generally the amplifier may work even without this zeroing. Yeah, so it may work without zeroing, but in this case we actually will have some we may have some non-zero voltage on the output when the inputs are interconnected and connected to zero. As to the chips or housings for the amplifier, so the three typical type of housings are demonstrated here. So one of the popular is so-called deep housing. For the deep housing has a legs going out, or contacts are going out of the chip with a pitch, I remember correctly, 2.58 lines, or 2.85 millimeters. Sorry, this is standard pitch of the deep package, and such kind of package is very well suitable for the prototyping using solderless boards, or for the prototyping because it's much more convenient to solder such a big chips. If you're going to get something small, so the SOIC surface mounted housings in a variety of types are available. So we could get nearly every amplifier. If we could get it in a deep package, we could get it in a SOIC package very often too. And the third, quite old-fashioned, 2058 housing that is this metallic box, but it have some advantage that the metal of the housing protects the internal circuitry of the op-amp from electric interference very well. This is sometimes such type of housing still sometimes are used. Another example is an amplifier LM538, which actually it's one of the most useful in our lab. We actually has a very limited number of amplifiers, and usually all the prototypes we do using LM538. So this is typical example of dual op-amp. It means it has a two separate amplifier in one chip. They have common power supply, so the plus and minus plus and minus legs for the connection of the power, they are common for both of these amplifiers, but they each has their own inverting and non-inverting input and the output, and the same for the other side. And so we have two op-amps. If I remember correctly, LM539 or 540, I don't remember exactly, but there is a next product in a line of LM538. This is a quad amplifier, but we have a deep type box, the deep type housing, where the four application amplifiers are placed in one chip. Well, okay, so to be able to calculate the uh, circuits when the amplifier is exploited. We actually use so-called ideal op-amp model. And for ideal op-amp model, we have actually following assumption. First of all, we assume that the gain of the amplifier is an infinite. As you understood, it's actually not a case in real life. It never could provide an infinite output. For the real amplifiers, the outputs, they are not certainly infinite. They are just very high. For the same LM, if I remember correctly, so this LM has a gain, call it open loop gain, if I remember correctly, about 10,000. So it's very big. But we could consider that it's just infinite. So the amplifier produces the output voltage as a reaction of the difference between input voltages. So one more, it's a differential amplifier. It means that the output is proportional to the difference between the voltage on the inverting input and voltage on the between the voltage on non-inverting output U2 and voltage on the inverting output U1. And this is U output voltage is actually made of this difference, U2 minus U1, times amplification. Of course, you already immediately may ask, well, does it mean that the voltage of the output voltage will be infinite if the amplification is infinite? And generally, the answer is no. But what happens? So when the difference between inputs is high enough and we have here output voltage which is close to the power supply, so then the output voltage doesn't change anymore. So the ideal op-amp is, not ideal, but real op-amp is characterized by so-called saturation. So when you have the difference in inputs high enough, the output grows until it comes to the power supply. Generally, the output of the amplifiers is not exactly equal to power supply, but it's limited by the power supply. The difference between the output and power supply line is a positive or negative, maybe up to 1.5 volts. Of course, there is some very good amplifiers, they so-call it rail-to-rail. The amplifiers which the most effective use the power supply. So for them, the difference between the saturation output and the power supply may be as low as 0.1 volt. So it's very close. But well, so so this is an ideal amplifier and ideal differential amplifier. That's why, despite of we presume that the gain is infinite, we still, let's say, we define this infinity. It's like this: that when the input voltage is similar on both inputs, then U1 and U2 are absolutely equal, and then we get this difference 8 U2 minus U1 is equal to 0. So then the output will be 0 too, despite the amplification coefficient is infinite. Of course, it's a little bit strange because why we do so, but because we use it as a model of the ideal amp, empirically we say that yes, it works. So when the inputs are equal, so the output generally should be 0. From the mathematical point of view, this output actually is not defined because we have to take an infinite gain and multiply it by 0. So the infinity times 0, thus here this is actually a typical unresolvable situation. But we presume that output should be 0 when the inputs are equal. Another feature of the ideal op-amp, we presume that input resistances are infinite. It means that when we apply a voltage to the input of the amplifier, there will be no current inside the amplifier. So no current flow in or flow out from the inputs. Of course, it's just approximation. It's an assumption. It's not the case for a real amplifier, but it's very close because the actual input resistance of the amplifier may be as high as some gigaohms. So the megaohms is absolutely normal, but sometimes together with a circuit, in the circuit, in the implemented circuit, the input resistance may be effectively even higher, so up to gigaohms. We consider that output resistance is 0. It means that we may load the amplifier with absolutely any load. What actually is not the case, because if we shortcut the output of the amplifier, it's with very high probability the amplifier will burn out. So it couldn't keep so high current. Nevertheless, we doesn't take into account that generally there is some output resistance in the amplifier. For the amplifier, they are not too high; they're about 40 ohm. We consider frequency band of the amplifier infinite. It means that we presume that the gain and other parameter, but mainly the gain, doesn't depend on frequency. What is actually not the case, and here we will have a dependence on frequency here. And the same we presume that we have no phase shift. Yeah, so when the input change, the output change immediately. Also, usually there is some phase shift, and we have to control this phase shift to prevent the op-amp circuits from oscillation. Well, so taking this ideal feature, we may formulate the two rule of thumbs. What we are using when we calculate the corresponding amplifier circuits. First of the rule of thumbs is, say, it's related to this infinite gain. So actually, if we have any really, we would have any really infinite gain. So what actually happens? So when the voltage U2 will be higher than U1, so that the output voltage will be positive and maximal possible. So it goes to positive saturation. When the voltage U1 is higher than U2, so the inverting input has a high voltage, the output will be -2, but it will be dropped down as low as a negative power supply, and nothing else happens. To prevent the amplifier from going to saturation, we are forced to use here the feedback, the negative feedback. So we somehow somehow connect, either through resistors, through capacitor. It's different ways how we do it, yeah. But we connect the output back to the inverting input. And what happens here? So if the output is growing up, this grown up voltage, part of the increased voltage, is passed back to the inverting amplifier. The inverting amplifier, when we have a positive voltage on it, this voltage will appear on the output with a minus sign. So it means output is growing through the negative feedback. It comes to the inverting input, and the inverting voltage on the inverting input reduce the output voltage. So that actually leads to the non-saturating operation of the amplifier. So output is not saturated when we have a feedback. So one more. Please, when we are going to understand what the operational amplifier circuit do, we have to check, is there any feedback or not? So as a feedback, one more, we understand that the output of the amplifier is connected to the input, and it's very important, to the inverting input of the amplifier by some circuit. There is a different way how to do this. We'll see it in a few moments. So when the operator works with a feedback, we say that it works in unsaturated mode. So it means the output will not be as saturated. Yeah, but in such a mode, the op-amp works in a manner when his input voltages are equal. So when the input U2 and U1 should be equal when the amplifier is with a feedback mode. It's okay. So the one was the first rule. So when the amplifier has a feedback and works in non-saturated mode, the inputs on both the both voltages on both inverting and non-inverting input are equal. The second rule is that when we consider the flow, current flow through the input, so they are always are zero. So that no current goes through U1 into the amp, no back, and no current go from U2 into the amp and back. So it's absolutely, so we use it actually as a second rule. So using these two rules, we may actually calculate whatever or design whatever op-amp circuit. So let's see some example, for instance, this one. So in the inverting amplifier. So first of all, so the connection is like this. So I have a resistor RE, RI, the first, and I have a resistor RF, RF for the feedback, and I apply my input voltage on this to this amplifier to the this resistor R1, RE input, and I measure what will be the output. So let's consider how do we do it. So first of all, do we have a feedback here? Is the output related to the input, connected to input? So please concentrate. Do we have a feedback here? Is the output of the circuit connected to the amp, connected to the input of the amp? Well, certainly we do. Take a look, yeah? Do you actually hear me at all? Probably I speaking and you don't hear me. No.
Yes, we can.
My phone is switched on. So please react a little bit. I just want to know whether you still alive and not asleep. Yeah, I could imagine that it's quite easy to go to sleep when you're sitting somewhere on the other side of the screen. Yeah, so we have here a feedback. So make sure, yes, make note that our output of the op-amp through the resistor RF is related to the inverting input. Actually, the notation Ri and Rf is because for the resistor for input and for resistor for feedback. And let's try. So if we have this feedback, so what we could say about the voltage in this point? The inverting input, non-inverting input, is related to the ground, to the zero of the circuit, to the circuit zero, and if it's connected to the zero, the voltage on the non-inverting input always will be zero. The question is which will be voltage in this point, or is marked by pointer now. We have to use this first rule, what I actually discussed it. So if we do have a feedback, then the voltages on the input, on the inverting and non-inverting inputs will be the same. If I have here a feedback and I have on a non-inverting input 0 voltage, which voltage will be here? We have a feedback. So that means that voltages on the non-inverting and inverting input should be equal. If on inverting input, they always will be 0 because it's always related to the ground, what will be the voltage here? Hello, wake up. Is it generally clear what does it mean connected to ground? Here? No. No, it will not be UI. One more. We already spoke. When we have a feedback, it's no matter how big RF is, no matter what the feedback is, it's important that there is a path for the current from the output of the. It's important that we have some path for the current from the output of the op amp back to the inverting input of the op amp. It means that we have here some kind of negative feedback. Yeah? That it's just from the name. Why we name it feedback? Because part of the current or wall current, no matter, yeah, is fed back to the input of the amplifier. So we have a feedback. When we have a feedback, the first op amp rules say that if we have a feedback, then the voltage on inverting and non-inverting inputs should be the same. Why they will be the same? Because if they become different, the output changes immediately. So what does it mean they are the same? They are not the same just because we want it. They are the same because the operational amplifier itself, via this feedback, controls the voltage on the feedback input in such a manner that it always will be equal to the second input voltage. Not because it's just a, how to say, it's not just declaration. There is some operation of this circuit. So the circuit operates like this. So if for some moment, what actually is happening, if some moment the voltage, for instance, on inverting input start to grow, it immediately causes the increment in the output voltage, and the voltage on the inverting input will increases too. So if this grows, this grows. If this falls down, this will fall down. So the amplifier itself, because of this feedback, will keep the inputs the same at the same voltage. And now I'm asking, if my non-inverting input is connected to the ground strictly, always at 0, what will be the voltage here? Лекция пошла. Позвонишь. Yeah, yes, it is. It will be 0 too. So if we put here +5, here will be +5. If we put here from some non-changing source, if we put here 2 volts, it will be 2 volts. If we -1, it will be -1. So they will be same. And this connection is very often is referred as so-called virtual ground. So this point is actually not directly connected to the ground, to the 0 of the circuit, but it's always will be at 0 because of the operation until our operational amplifier is working. Of course, if it doesn't provide a power supply to this amp, it will not be 0 here. But if it has a power supply, it's operational, it's not damaged, so it will keep the voltage here equal to voltage here. And if we have here ground or 0, we will have here 0 too. So the voltage will be 0. If a voltage here is 0, we know it. So it means that we very easily made to calculate the current through the resistor Ri. Yeah? Because we have from one side, we have an applied voltage U input. From other side, we have a 0. That means the difference of the voltages between voltages here and here, or so-called voltage drop over this resistor, will be just Ui. So this one minus this one. Here we have a 0, then we get just Ui. And therefore, because of the Ohm law, the current which flows through the resistor R, input resistor Ri, will be equal to the voltage on this or attached to this, applied to this resistor, and divided by the resistor value itself. So this is the current which flow here. Ui is the input voltage. But now when this current flow, here we have some kind of 2 ways. Part of the current may go inside the op amp, and part of the current flow through the resistor RF, so the feedback resistor. What could we say about the current which goes into the amplifier? Let's remember second rule. Both currents which go through the inputs into the amplifiers are 0. So that means that the current which could go through the amplifier is 0, and it means that all the current which flows through first resistor will go through the second resistor too, because there is no way for the current to go inside the amplifier. And then it means that all this flow, all this current should go like that way. When it comes to the output, yes, it is not prohibited for the current to flow inside the amplifier or outside of the amplifier. And finally, this current flowing through inside of amplifier will finally come to the ground somewhere inside, no matter where. But actually, what we know that this current and this current are the same. Let's consider now the second resistor. So here we have some voltage U0, U out, sorry, and here we have 0. For the current to continue flow in the same direction, in the same direction that is shown here, so the current flow in and then go through here. And for the current to flow in this direction, what should be the polarity of the output voltage if here we have 0? Plus or minus?
Should be minus.
It should be minus, yeah. Otherwise, so because the current couldn't flow from minus to plus, it should flow from the higher voltage to lower voltage. And if we have here 0, so then we need that output should be lower than 0. So it's negative, it will be minus. So that's why we write here a minus. And now we know, first of all, that the voltage drop will be negative, but the second, that the value of this drop will be U0, just U0. Because one more, here we have 0, here we have U0. So the difference is just U0. Knowing this, and we may use the Ohm law one more to calculate this U out, the output voltage, as a current which flows through the resistor, through the feedback resistor, times the resistance of the feedback resistor. So this is Ohm law for this part, and minus just emphasize that the output voltage will be negative. If we now put here the current calculation of the current from the input, we will get the relationship between output voltage and input voltage. We see that the output voltage will be proportional. First of all, it will be negative, inverted in respect to input voltage. When the input will be positive, the output will be negative, and vice versa. And it is proportional to the value of the voltage on input, and the proportionality here is expressed with this ratio RF, R3 divided by Ri. So this ratio, if we take this feedback resistor bigger, with a bigger resistance than the input resistor, so we will get this ratio higher than 1. It means that output voltage will be bigger than an input voltage. And actually this ratio is nothing else than the gain of this amplifier. So the gain of inverting amplifier is a ratio between the feedback resistor resistance and the input resistor resistance. So this is an example of how do we calculate the amplifier circuit. So we exploit these two features. So if we have a feedback, then we have this equal. We have an equal voltages here on inputs, and when we have a current flowing around the amp, so there is no current is flow into the input or flow out of the input. So we use these two features. Well, what actually else I want to note about this? One more thing about my expression about this ground concept, voltage in respect to ground, and so on. Is it clear? What does it mean that we have some voltage, some input connected to the ground? What we understand under this ground? Do you need any comments, or is it clear totally? Okay, so we just remember that we always have in the circuit some point what we declare. This is a 0 point. Yeah? For the bipolar voltages, for the bipolar power supplies, this general ground point will be just this point in respect of which we have a plus and minus power lines. For the unipolar supply, the ground very often is connected to the minus of the battery. But at some point, what we consider as zero. In some extent, it's quite voluntary how we select this point. But usually we build all our circuit bearing in mind we have this 0 point. And they appear when we connect some measurement devices are connected to this point, and say power devices are connected to this point, at least with one electrode. Okay, so here is an example how the input-output slope plot of this amplifier looks like. So here we have the input voltage, here we have an output voltage, and this is an example when we provide the power supply plus minus 13 volts. Yeah? And the amplifier is of the class of this LM of this 741 or our LM583. So it's not very high class amplifier, and that's why the maximal voltage it could produce it's about 2 volts lower than the power supply. They are not perfect rail-to-rail amplifiers. They are provide a little bit less by some 2 volts less maximal output voltage. And here we see that in certain range of the inputs, it's actually provide a linear regularity between the input and output. But from the certain level of the inputs, or we actually reach this saturation voltage, and when we increase more the input voltage, still the output will be the same because of the saturation. So this actually defines that we have a certain range of input voltages to work with the amplifier in a linear mode. Some example of the application, how we do use inverting amplifier. One of the useful circuits here is a summing or summating amplifier, which actually allow us to get a sum of the input voltages. The design of the amplifier looks like this. So we generally have the same inverting amplifier, but it has several inputs. They all are connected through the corresponding resistors to this inverting input. And what actually happens? The voltage here is always 0, always, because we have a feedback and because of the first rule. It's always voltage here is always 0. That means that when we has some distribution of voltages on the inputs. So all this U1, U2, U3, and UK is different. Each of these voltages may cause some current flow through the resistor R1, R2, R3, and so on. If its voltage is positive, and here we have 0, the current goes that way. If the current was negative, the current goes that way. But actually, and why it's important? So it's important that the op-amp always keeps this point as equal to 0. Due to this, the currents through the resistors R1, 2, 3, and on, it doesn't depend on what is the voltage here. It's always 0. And these currents are defined only by the voltages, these input voltages. It may be positive. In this case, current flows that way. It may be negative. In this way, current flows that way. But all these currents, they are summed together, adds together in this point, and then it depends on which currents are bigger. If the positive currents which flow that way are bigger, they overforce, let's say, currents that go back. So actually, all these currents will be added together algebraically. It means taking into account the sign. The positive and the negative, they all add together and flow through the resistor RF, so the feedback resistor. And that's why the output voltage will be just equal to the output resistor times all the sum of all the current, and every current is calculated as the input voltage divided by the corresponding input resistance. I forgot here minus, of course. There should be minus, but if I'm interested in the absolute value, not just in sign plus or minus of my voltage, so I actually may just omit this minus. I have to bear in mind that there will be some inversion. There will be, if those all are positive, as here I have all negative voltage. And this is an example. So what actually I have got? I have got that the output voltage here, it's a something proportional to the sum of input voltages. I may select all these resistors R, I, all equal. They all may be equal, and may be equal to the RF, for example. In this case, my equation here reducts or reduces with just an expression that the output voltage is just a sum of all input voltages. So this is a called summating amplifier. So we may get a signal which is equal to the sum of other signals. Some example why, for instance, I may need such kind of summating amplifier. For instance, I have some physiological or any other signal which is changing on the base of big DC components. I have a DC component, and then on the top of this DC component, my useful signal is changing. So my useful signal is exclusively on this, only these small changes. I'm not interested in this DC component. If I try to amplify my signal together with the DC component, the DC component will be amplified as well. So, and what actually happens? Could you imagine if I take this shape and presume that it's drawn on an elastic sheet, and I try to pull it out? So it actually goes up. Or if it would be easier for you to just think what happens if I multiply by some number this curve. So what happens? It goes up, but the DC, this basement, grows up too. And because of the basement growth, all this my graph multiplied by something will very fast reach this maximal voltage what the amplifier may produce. Over 10 volts, it already goes to saturation. And you actually understand there and feel that my base will be amplified. This small oscillation will be amplified too. But on the background of this big base, this amplification will be very teeny. I couldn't get a good amplification, because if I got a high amplification to see the details of this small changing useful signal, it actually goes over the saturation, and I will not get anything useful. So what I could do, I could extract this base, the constant voltage, from my signal. When I do it, if I extract it, the resulting signal looks like this. And now I may use quite a high gain to amplify it. So here is just an example. So there is initial signal. Here I subtracted this constant component before amplification, and here I amplify it with an inverting amplifier. And then, as you see, that here I have a very big, amplitude, very big range of my amplified signal, which actually allow me to see details in this signal and so on, and work with them more effectively. And here's an example how we actually could do this. Yeah? So I use a summating amplifier circuit. So I put here my useful signal, and here I may regulate by myself the voltage on this point. In fact, by moving the slider of the potentiometer, which is connected between positive and negative poles, I may actually change the voltage on this input. Yeah, here. And due to this, I actually introduce here some input voltage that will be extracted or subtracted from the total voltage. In this case, yeah, our output will be feedback, yes, and so the output voltage, yes, but we still have an amplification here. So if I define two resistors, here are input and these are background, to extract the background. So the output, the current, what comes here will be this one. So it's a current through this branch plus current through this branch, and then I add them together. They sum together and multiplied by RF provide me the output voltage. So if I select UB negative, I may actually subtract, so add some negative constant to my signal and shift it to 0. Hereby I actually extract this unuseful useless DC component. So, and some other examples of the amplifiers before we stop. So this is another example of the amplifier. So one more, try to analyze this. Do we have here the feedback? Yes. And for this feedback, which actually realized or made like just a wire connecting without any resistor inside, just directly connect output to the input. And we put here the input signal on the non-inverting input. So if we have a feedback, what we could say about voltage here and voltage here? They are the same. So it means that here we have an input voltage. But if this voltage here is an input voltage, it means that the output voltage should be equal to the input voltage too, because they are connected just to one wire. One of the principles of the circuit design, so when we draw a wire, we presume that there is no any voltage drop over the wire. So if we have some voltage in one end of the wire, this in respect to the ground, the same voltage will be always all way along the wire. Of course, in real wires, they are not with the infinite conductivity. They have some voltage drop. But when we just roughly sketch the circuit from the very beginning, we ignore it. We need to take a real drop in the wires if we consider, let's say, some kind of high-end or very, very delicate equipment, or when really such small voltage, some small resistance may play a role. In this case, it still cannot play a role. So, and then we actually find that, yes, because we have a feedback, the voltages here and here should be equal. Because voltage here is U input, the voltage here should be U input too. But if as this input is connected to the output with just a wire without any voltage drop, nothing else, yeah, we just have to conclude that voltage here and here will be equal to, because of the feedback. And the result actually is that we have some circuit when the output voltage is equal to the input voltage. As they are equal, the circuit is named follower. So it's actually output voltage just follow input voltage with a unity gain. There is no any gain. No voltage. Sorry, it is not correct to say not any gain. There is no voltage gain in such a circuit. So if we apply some voltage as an input, the same voltage will be that output. The question is, what is the reason of such to use such a amplifier, which actually has a voltage gain equal to 1? Does it amplify anything? And when we could use it? And why we need such a circuit? What is the purpose of such a circuit? The answer is that here, if we compare with a inverting amplifier, so if we put some voltage here on the input, this voltage causes the current E to flow into the circuit, and this current will depend on the voltage and the resistance Ri. So actually the current which flow inside will be the input voltage divided by Ri. It means that the input resistance of this inverting amplifier will be just Ri. So if our power, our signal source, what provides us this voltage Ui, is powerful enough, it has enough power to keep such high current, such a current like Ui divided by Ri, our circuit works well. But if our source of the signal is very low current source, sometimes it couldn't keep such a high current, which is required by the combination of voltage Ui and resistance Ri. And in this case, our inverting amplifier just doesn't work because our source could not provide the necessary current. Yes, we may fight with it. We may try to solve this by adding Ri, to taking Ri as high as possible. But if it will be high, Ri is high, our gain may drop lower than 0. Of course, you may already argue that we could increase the feedback resistance. Yeah, you could do this, but you usually in practice, in theory, we may even increase it up to infinity. Yeah, in theory, but in practice, when the feedback resistor is too high, the output signal, output of the amplifier will be subjected to the very high noises. The higher is feedback resistor, the higher is output noises. It's just because the parasitic, fluctuating bias currents that still flow through the amplifier input. They add quite a big voltage drop over a big feedback error. So this current may circulate in that way and cause additional voltage drop. The temperature effect, the temperature current or temperature actually, yeah, current, which is produced in any resistance itself. It's so-called a temperature noise, current-related, temperature-related noise. Actually, it's expressed as a chaotic current, which may change direction and amplitude and oscillates here over the resistor RF. If our RF is high enough, this oscillating current causes quite a significant voltage oscillation in the output. So, and in practice, the feedback resistor very seldom is taken more than 100 kilo. And even 100 kilo, it's a little bit much. 50 kilo, it's okay, fine, up to 50 kilo. If it goes to 100, it's this heat noise current starts to play a quite noticeable role. So that's why we couldn't take it very high. And what should we do? What could we do to have still some amplification, to have some gain, and still have a high resistance? Actually, nothing to do with inverting amplifier. It's always have input resistor resistance equal to this resistor resistance. And the follower, we know that following this second rule, the current this is flow inside the follower through these non-inverting inputs will be extremely low, because we have nearly infinite input resistance for the amplifier itself, and it will be very low, very high. In fact, in practice, as I said, it's is up to several, even up to several kilo. And the current itself, there is some parasitic current which flow inside, but this current is in order of nanometers, and for a very good amplifiers in order of picometers. So we actually could say that there is no current. So actually, what the follower do? It allows us to use some voltage source or signal source, which is very poor in current, which couldn't provide a high current, could provide only voltage. There is plenty of such sources. All the normal chemical elements, ethylotic elements, which provide an electromotive force ethylones. It's thermocouples. It provides some voltage drop when they are heated. It's biopotential sources, so cells, humans, animals, they couldn't keep a very high current of due to biopotential, caused by biopotential. Yeah? But they could keep voltage, and then we use something which have a very high input impedance, input resistance, to prevent the these sources from overloading. Well, and in fact, we use the follower when we need to separate two circuits, to prevent that one circuit, the input of one circuit, affects the output of another circuit. So we sometimes use it as a buffer between one circuit and another circuit. And in fact, the follower indeed has a gain of 1 for the voltage, but it has non-zero gain, which actually very often are not calculated even. Yeah, it has not non-zero gain, non-1 gain for the current. In fact, the follower is a current amplifier. So it's use a source, it's take a signal from the source which couldn't provide a high current, and provide the output with the same voltage, and the output of the follower may keep a much more higher current. So in some extent, it's a current it's amplifier current, and due to this, the power of the signal. We may a little bit update the follower to have to still to keep its good feature, very high input resistance, but still add some non-unit gain for it. And the resulting circuit is named as a non-inverting amplifier. So we actually connect the feedback, we introduce a feedback resistance in the feedback loop, and we connect an inverting input to the ground. So the consideration of this amplifier is the following. We have a feedback. If we have a feedback, it means that the voltage in this point will be equal to voltage at that point between inputs. The difference, there will be no difference between inputs. They will be at the same voltage. And if the input, non-inverting input, is at the input voltage, it means that voltage here will be equal to the input voltage too. From this, we just write down the relationships between the output voltage and current through the chain of this resistor chain. So if I have output voltage here, some output voltage, and they have to flow through the current which this voltage will cause, will flow through the resistor RF and RI, so from both of them. We know that it couldn't turn here inside into the amplifier because of the infinite input resistance. The second rule, there is no flow inside the amplifier. So, and then from the Ohm law, the current that flow here could be expressed like this: output divided by Ri plus Rv. From the other hand, looking just on the resistor Ri, so when this current I is flowing through this chain, and by the way, it flows through the resistor Ri, and I may calculate the voltage drop over the resistor Ri. It will be just I times Ri, the current I times the resistance of this resistor, and it will be voltage drop over this resistor. But I know that from one side the voltage is 0. It means that from the other side the voltage should be equal to this voltage drop, and it will be equal to this I times Ri. But I know from another hand, as I have a feedback, I know that this voltage and this voltage are equal, and it means that voltage here is just U in. So U in is equal I times Ri, and putting here the U in, regrouping the terms, finally I get such a relationship between the output voltage and input voltage. And the gain of this amplifier will be Ri plus Rv divided by Re. So what is important about this gain? It always is bigger than 1. It could be less than 1. Yeah? Even if Rf is 0, then the gain will be 1. So we just come back to this follower. If the feedback resistance is non-zero, the gain always will be higher than 1. So this is I'll call it non-inverting amplifier. I think we stop for today. There is no task for you. Still, probably you may review your notes on the electronic course to make our further discussion more fast, probably. Yeah? And we discuss next time the very important type of the amplifier, so-called instrumental amplifiers. This is very important because it's actually the center of any physiological measurement device. So it's all based on the on the instrumental amplifier. And I hope that we will have time tomorrow to see a different kind of function, or the next time to see the different type of functional circuitry, like a logarithmic amplifier, rectifiers, which are used as a component in the different kind of measurement devices. Okay, thank you for today. Do you have any questions? So, if you have no questions, so probably we stop for today, and see you next use the